Unit 10.1, Eulers' equation for elastic buckling. In this unit, we will focus on the outcome, show an understanding of simple buckling phenomena. In this lesson, we will focus on being able to calculate critical buckling load for members in compression. In Unit 3, we covered stress and deflection in axially loaded members. Normal stress was calculated as the internal force divided by the cross-sectional area. If the normal stress exceeded the yield strength of the material, then the axial member was considered to have failed. For axially loaded members in compression, a failure mode other than yielding is possible. It is buckling. Let's consider this member, which is axially loaded in compression. We will call it a column because it is oriented vertically. And we're going to say that this is an ideal column, which is that it is perfectly straight, its material properties are homogeneous, there are no imperfections, and it is loaded through the centroidal axis. The member is pinned at both ends, but only horizontal deformation is restrained at the top. Now, as this load is gradually increased, it will get to the point where the member becomes unstable. There will be two possible geometric configurations of this member. First is standing vertically, where the internal stress is just a compression stress, or it could buckle, in which case the internal forces will be both normal forces and a bending moment. Buckling results in some significant deformation in the lateral direction. When the member takes on this buckled shape, the yield strength of the material is not necessarily exceeded, and additional load could potentially be applied before material failure results. However, depending on the purpose of the member, buckling could result in its inability to continue to perform its intended function. Leonard Euler developed the equation for determining the critical load that will bring the column to the verge of buckling. This is the equation. P critical, this is the critical buckling load, is equal to pi squared E times I over L squared, where E is the modulus of elasticity, I is the moment of inertia of the cross-section, and L is the member length. It might seem odd to have pi squared in this equation. It turns out that this equation is derived from the solution to a homogeneous second-order linear differential equation, and the derivation of this equation can be found in most any mechanics textbook. The units on critical buckling load are force units, either pounds or newtons. Recognizing that normal stress is force divided by area, and also identifying r, the radius of gyration, which is equal to the square root of the moment of inertia divided by area, we can rewrite the critical buckling load equation as critical buckling stress. This equation turns out to be very useful in design. Note that Euler's equation shown here is restricted to the buckling of members that are pinned at both ends. One more thing to note. Consider we have this axially loaded member. These rigid plates at top and bottom prevent lateral translation, but do allow rotation, so they will be acting as pin restraints. The cross-section of this member is rectangular. There are two principal axes for this cross-section, the XX and YY. We know from previous units that the moment of inertia about these two axes are different. The XX axis will be the strong axis, and the YY axis will be the weak axis. XX axis will have a larger moment of inertia. The YY axis will have a smaller moment of inertia. When this member buckles, given that we have uniform support conditions, buckling will occur about the weaker axis, which in this case is the YY axis. What this means is when we calculate the critical buckling load using Euler's equation, we will use the weaker axis moment of inertia in that equation. And we're done.